At the end of our last chapter, we were talking about the acidity or basicity of salt solutions, right? We said a salt solution could be acidic, basic, or neutral depending on whether the cation or anion in the salt were acidic, basic, or inert, right? If the salt were inert, it was going to be a neutral solution. I do want to just look at that again in a little bit more detail, and then we'll calculate the pH of salt solutions also. So we'll start by just re-looking at neutralization reactions. Remember, our acid-base neutralization reactions result in water and a salt. And we're going to go through and look at our strong acid, strong base, weak acid, strong base, strong acid, weak base, and then if they're both strong. So our first one, a strong acid, which I'm probably just going to use SA, strong base, SB, reaction. So these were the ones that resulted in salts that were inert, right? Salts that led to a neutral solution. We had an example. We can use hydrochloric acid, one of our strong acids. I can react it with sodium hydroxide, one of my strong bases. And we form water plus sodium chloride. Water, a pure liquid, sodium chloride being soluble in water. If we were to write our ionic equation for this, right, my hydrochloric acid is completely ionized. I do know that protons in water actually are going to attach themselves to water, so I'm actually going to write hydronium ions instead of H+. We know that that's more accurate. Cl-, both of those aqueous. Sodium ions and hydroxide ions. Water is a pure liquid. I am going to need a 2 now to balance it because I'm writing hydronium ions instead of just protons. And then sodium chloride is my salt. It is also dissociated. And then we had said that sodium was a spectator ion, so that gets canceled out. Chloride is also a spectator ion, and that gets canceled out. Right? Chloride being the conjugate base of a strong acid, so it has no affinity for protons. Right? It's not going to be basic. Sodium, the metal for my strong base, not acidic. Neither one of those are reacting, and we can just cross them out to give us this net ionic equation. And this actually does establish equilibrium. If we look at it, it's actually the inverse to my KW reaction, right? Remember the ionization of water. If I wanted to write KW, it's hydronium ion concentration multiplied by hydroxide ion concentration, right? We had water plus water, both of those liquids reacting to form hydronium ions plus hydroxide ions. And then when we write our equilibrium constant expression, right, it was concentration of products over reactants raised to a power equal to their coefficient, but I don't include water because it's a pure liquid, right? Its concentration isn't changing over time. If we were to compare now this, right, to this, all I'm doing is I'm swapping my reactants in my product side. So now if I was to actually write an equilibrium constant or equilibrium constant expression for this, we'll just call it K for now. I'm actually just going to have 1 on the top, right? Because it's always products over reactants. Products in this case is water. I'm not going to include those over the concentration of hydronium ions multiplied by the concentration of hydroxide ions. And we're going to put an N here. We're not going to do much with this, but I just want to talk about it for a couple of the reactions. So N for neutralization, right? If I was to write my net ionic equation, which is this, for an acid-base neutralization reaction, right, and using a strong acid and a strong base, and then write my equilibrium constant expression for that neutralization reaction, this is what we're going to get. So N for neutralization. And that's, of course, 1 over Kw, right? So that's actually 1 times 10 to the positive 14th, right? It's mostly products at this point, right? That's a big number now, the inverse of Kw. So a large value, right? Remember, a large value for my equilibrium constant means that it's mostly products. At equilibrium, right? It's product favored at equilibrium. So I mostly have 100% completion, right? It's not 100%, but it's really, really close, right? That's a pretty large value. It's much larger than 10 to the third, which is kind of our cutoff for whether or not it's big. If I was to look at the pH of my solution, it is going to be neutral, right? Neither sodium or chloride ions are going to react with water to produce hydroxide or hydronium ions. All I have is water reacting with water, producing hydronium ions and hydroxide ions. So as we said previously, my pH is going to be equal to 7. Right? Both the cation and the anion are inert. Looking at a weak acid strong base reaction, so Wa strong base, and I am going to jump right to the net ionic equation. We have looked at these previously. So we know that our weak acid is largely undissociated. So if I was looking at HF, right, it's mostly HF. Some of it is F- and hydronium ions, but my percent ionization is pretty small. So mostly undissociated acid. So I'm going to keep it that way. And I'm just going to use HA as a generic acid. My strong base is completely ionized or dissociated. So I can use hydroxide ions for that. So when I look at my reaction for this one, I have HA for my acid, mostly undissociated, so I'm writing it in that form, plus my hydroxide ions for my strong base, which is mostly or completely dissociated, and we form water, plus my conjugate base. My cation from my base was a spectator ion. It got canceled out, right? Remember that the cation from a strong base is inert, so it's not part of my problem here. This is basic. So it does react with water to produce hydroxide ions and the conjugate acid. Our pH then is going to be greater than 7, right? Again, that conjugate, I guess it's not even conjugate here, I shouldn't say that. It's the anion from my salt, right? It's a neutralization reaction. So the anion from my salt reacts with water to produce hydroxide ions and a conjugate acid in that case. Kn for this then is going to be the product of the equilibrium constants for the two reactions that we add together to get this net equation, which is kind of a mouthful. And it's easier to just kind of show you real quickly. So I do have an acid, right, HA. It does react with water. We've written this equation quite a few times already, right? This is my acid dissociation equilibrium equation. And if I was to write my expression, I would set it equal to Ka, right? So this reaction, as far as its extent, right, is it mostly products, mostly reactants, is defined by Ka. I also have my acid reacting with my base. That's supposed to be a negative charge. and that's producing my 2 water molecules. I am writing that equilibrium arrow, but it is mostly products. And we said that was 1 over kW a little bit ago. If I was to add these 2 equations together, I have 1 water molecule canceling, and I have my hydronium ions canceling, and then what's left, HA plus hydroxide ions going to water plus A minus, right? This equation that I get when I add these together is this net equation. So Kn for that net equation is the product of these 2 equilibrium constants. So it's Ka over Kw for a weak acid strong base equation. And we have seen this concept before. I just didn't really talk about it. So we had the relationship between Kw, and we said that was equal to Ka times Kb. Where that comes from, if I was to take an acid, right, weak 1, react it with water. Again, I'm just writing my acid dissociation equilibrium equation, right? That's defined by Ka. And then remember the conjugate base here is basic. So I'm going to write a base dissociation equilibrium equation. Again, something we've written quite a few times already. And if I was to write my expression, I always set it equal to Kb. And then if I was to add these 2 together, A minus cancels, HA cancels, and what's left is water plus water going to hydronium ions plus hydroxide ions, which is my Kw expression, right? My ionization of water. So Kw, right? Let's actually write it since we started. Right, this is Kw. Kw is actually equal to the product of those 2 equilibrium constants. And that's what we're doing here. We're just saying my neutralization constant, right, is equal to the product of the 2 equilibrium constants for the reactions that we add together to get it. And that's where this came from also. I just gave it to you without showing you that, but that is where it's coming from. So a strong acid, I had to check to see where we were. I'm going to start abbreviating on you now. Weak base. And again, I'm just going to go right to the net ionic equation. At this point, I really hope that you guys can do that, right? We spent quite a bit of time on salts. We know what cations and what anions are inert, right? We know which ones are spectator ions, and we can ignore. So if I have a strong acid, it's really only the hydronium ions that I care about, right? HCl is going to be H plus and Cl minus. I don't really care about Cl minus. It's not going to react with water to produce an acid or a base. It's inert. And then the hydrogen ion is really hydronium ions, right? It's going to attach itself to water. So if I have a strong acid, H3O plus, that's really the part that we care about. My weak base is largely undissociated, or if it's, you think about accepting protons, it hasn't accepted most of those protons. So I'm just going to do a B. I do get water. And then it's only the cation from my salt that I care about, right? If I had my anion here, right, it would be inert, it would be a spectator ion, and I would just cancel it out. So we're just going right to my net ionic equation. This, of course, is acidic. It can react with water to produce hydronium ions and a conjugate base. So we had said previously that my pH is going to be less than 7. And then looking at Kn real quickly for this one, I have my base reacting with water because it is an aqueous solution and water is acidic, right? It can act like an acid, I should say, right? It can accept or donate a proton. And then this would be defined by Kb, right? If I was to write my equilibrium expression for that, I would set it equal to Kb. This was my base dissociation equilibrium equation. And then I have water. I have my acid reacting with my base, to produce 2 water. This was 1 over Kw. And then if I cancel stuff out, again, 1 water cancels. My hydroxide ions are going to cancel. And then what's left, right, is my hydronium ions, my base going to water, and the BH plus, right? Those things that I just circled gives me that. So I know that Kn, I'm not going to rewrite it, is equal to Kb over Kw. And again, I'm not going to do a ton with Kn. I just want you to know that there, you can define a neutralization equilibrium constant and then kind of where it's coming from. And then again, based on the size of it, we can tell the extent of the reaction. So if I do have you solve for one, just is it mostly products or is it mostly reactants, right? This one is always equal to this number at 25 degrees Celsius. So almost completely to completion. That was kind of redundant. These ones you would have to be given some values, but you're taking, a small number, dividing it into something that's not quite as small. Okay, one more. Number 4, a weak acid, weak base. Again, these are neutralization reactions. I didn't write that last time. So this time, my weak acid and my weak base are largely undissociated or unionized. I am going to get water and a salt. And instead of just giving you the net for this one right away, we're going to actually do the equations that add together to get it, so you can kind of see where it's coming from. So I have my weak acid. I'm just going to use HA again. You guys are probably getting tired of writing these equations. So Ka, my base also reacts with water. To give me hydroxide ions plus BH plus, so Kb, and then hydronium ions react with hydroxide ions to give me 2 water. And then we're going to add this together. This is 1 over Kw. Almost forgot it. So kind of lots of things to cancel this time. My hydronium ions are going to cancel. Both of my waters are going to cancel. Hydroxide ions are going to cancel. And that, I think, is everything. Which leaves me with my weak acid plus my base. And then we're really just showing the salt here. But again, remember, these are in aqueous solution, so there is, water also. So I do have something that's acidic. I do have something that's basic, right? So then the pH of my salt solution is just going to depend on the relative acidity or basicity of that cation and anion, right? If the Ka is equal to the Kb inert, neutral solution, they're not inert, they are reacting, it's just they're reacting equally. So I end up with a solution that's neutral. And then if Ka is bigger than Kb, acidic, Kb is bigger than Ka, basic. And then if I was to look at Kn for this, so many equilibrium constants. Again, it's the product of these. So what I want to spend a little more time on is actually just calculating the pH of these solutions, but I did want to talk about the neutralization just in a little more detail than we had previously. So just kind of, again, beating stuff to death. Strong acid, strong base. When I write my net ionic equation, which I really want us to be, pretty proficient at doing, it's going to save time if you can go right to that net ionic equation. So my net ionic equation is essentially the acid, right? It's only the hydronium ions or H plus that we really care about. My anion's always going to be inert. the hydroxide ion from my base. So anytime you have a strong base, just think hydroxide ions, and that's going to produce water. I would have a neutral solution because I would just have water reacting with water to produce hydronium ions and hydroxide ions. So pH 7. Weak acid, strong base. So jumping right to my net ionic equation, my weak acid is going to be largely undissociated. My strong base is completely dissociated. We don't care about the cation. It's going to be inert. So I only care about the hydroxide. I end up producing a salt in which the anion is basic. So my pH of that salt solution would be greater than 7. Looking at my strong acid weak base, my strong acid, H3O plus, again, if you have a strong acid, just think H3O plus. If you have a weak base, it's largely just in its normal base form, right? It hasn't accepted that proton. I'm going to produce water, and then the cation of my salt is acidic. The anion part, this would be a salt. I'm just writing net again. Remember, this is my net equation. So, I would have, again, A minus here. I would have A minus here. So this would be my salt solution. But again, I'm just going right to the net equation, so I'm ignoring that part. This is acidic. It would react with water. I would produce hydronium ions, so an acidic pH. And then with a base, it's essentially both of those, largely undissociated, right? And then my salt, I have both something that's acidic and basic. So just the relative strength of those two to get my pH. I do want to go through a few examples where we actually calculate the pH of our salt solution. So instead of just saying that it's acidic, basic, or neutral, actually get a value for them. So we're going to calculate the pH of a 0.10 molar sodium fluoride solution. And we do need an equilibrium constant for this. I'm just going to give that to us after. I want us to kind of think through this problem first. So kind of the first part is we need to figure out what part of that salt is going to react with water. And then we need to write that reaction and set up an ice table. So really the first step is doing what we did in the last chapter, is breaking the salt apart, determining that this is inert, and that this is basic, right? It's not an anion of a strong acid, right? It's the anion of a weak acid, which is basic. It is going to accept a proton and form hydroxide ions and HF in this case. So because the sodium hydroxide is inert, that part we're just going to ignore. So the part that matters, right, the part that we need to solve the problem is going to be this. So we're going to write our base dissociation equilibrium equation. And then that's what we're going to use to solve our pH. So kind of step one, analyze your salt. What part of it is reacting with water, in this case F minus, and then write that equation. That's the equation that you're going to use then to answer the question. We are given the Ka for this one. This is the additional piece of information you were missing. For HF, I should stipulate that. It is 7.2 times 10 to the negative fourth. And because I wrote the base dissociation equilibrium equation, what I need is Kb. So we do have to determine Kb, and we can do that by just dividing Ka into Kw. So we'll do that. A lot of times, if you look at values, because that's where I get these from, is I have a table, it doesn't actually give me a value for F minus. It doesn't give me a Kb for it. It actually gives me the Ka for HF, and then I would do this step to get the value for you. I'm just grabbing my calculator here, which is what that racket is. And I'm typing it in. I'm going to double check it. And I'm getting 1.4 times 10 to the negative 11th. You would set up your little ice table. So I have an initial concentration of 0.10 molar, right? Where I'm getting that from is this salt, right? If we were to write a reaction for that, NaF aqueous, right, separates into Na plus F minus, and then because it's a 1-to-1 ratio, right, because I have coefficients in 1 in front of all of that, whatever my concentration of this is my concentration of this. Now be careful for reactions that aren't 1-to-1, right? If I gave you something like strontium fluoride, now I would have 2 fluorides for every 1 SrF2. So just be careful for that. It's not always 1-to-1. In this case, it is. So whatever my concentration of sodium fluoride is my concentration of fluoride ions. But again, just make sure that it's a 1-to-1 relationship when you make that comparison. And then just our normal ice tables, we lose some unknown amount. I'm going to write 0.10 minus x, but then when I set it into my expression to solve for x, I am going to ignore that minus x because my Kb is small, right? There isn't, I do have some Kas and some Kbs that are not smaller than 10 to the negative third. They do exist. So you can't always ignore them, but most of them are going to have that Ka or Kb that's small. So then solving for x, I have 1.4, not 14, 1.4 times 10 to the negative 11th equal to x times x over 0.1 minus x, but again, I'm going to ignore that point, or that minus x, right? Because my Kb is small, it's negligible compared to my initial concentration. Solving for x, we've done these quite a few times at this point. In fact, I would assume that a few of you, if not most of you, could probably just set this up without even writing this table at this point. And I'm going to double check that because I was talking while I was typing into my calculator. And I got 1.2 times 10 to the negative 6. And then this is where you have to be careful, right? I wrote a base dissociation equilibrium equation. So X is equal to my hydroxide ion concentration. Also HF concentration, but we weren't asked to solve for that. We were just asked to solve for pH. So this is where you can do this one of two ways. I can divide this into Kw to get the hydronium ion concentration and then take the negative log of that value. Or I can calculate the POH and subtract it from 15, which is how I'm going, or from 14, sorry, which is how I'm going to do it. So negative log of 1.2 times 10 to the negative 6. Gives me a 5.92, so 2 digits after the decimal point because I want 2 significant digits, and then 14.00 minus 5.92. I get 8.08 for my pH. We're going to do one more example, and I want you to try it on your own and then we'll do it together after that. So we're going to calculate the pH. Of a, let's just do 0.1 molar again, ammonium chloride solution. I guess you need to be able to read it. And then if I'm going to send you on your own, I need to give you an equilibrium constant right away. So let's, the Kb of ammonia is 1.8 times 10 to the negative fifth. Okay, so please hit pause, try to solve this on your own, and then when you're ready, hit play again and we'll go through it. Alrighty, so hopefully you did that. So I do have a salt solution here, and I have ammonium ions and I have chloride ions. Chloride ions are the conjugate of a strong acid. These are inert. They're not going to react with water, so they're not going to contribute to my pH. So in this salt solution, the only part that I'm going to care about are my ammonium ions. And those are acidic. They're going to react with water, so that's the equation we're going to write. To produce hydronium ions plus my conjugate base. Because I wrote an acid dissociation equilibrium equation, I do need a Ka. I'm given a Kb, so we do need to solve for that. Oop, I added a 0 here. Sorry, I'm just kind of squishing it in here. So grabbing my calculator. And I get 5.6 times 10 to the negative 10th. And then I'm going to actually do this without writing the ice table. And by all means, still keep writing it. It's just I assume you've gone through it already and we're just kind of checking your work. But I do know that my initial concentration of this is going to be 0.1 molar. Right? When this dissociates, there's one ammonium ion for every one chloride ion. So the concentration of my salt is the concentration of my ammonium ions. So if you're making your ice table, you'd have 0.10 molar here, don't care, 0 and 0, minus x plus x plus x. Because my Ka is small, I would ignore that minus x for this equilibrium concentration. And then when I go to plug that in, I would have my Ka equal to the concentration of hydronium ions multiplied by the concentration of ammonia at equilibrium, so x times x, over 0.10 minus x, but again, we're ignoring that minus x. So solving for x, typing into my calculator here. And I got 7.5 times 10 to the negative 6. I do want to check my math here. I got the same number. And then that is my hydronium ion concentration, right? If you had your ice table in front of you, X is equal to this. It's also equal to this, but this is the one that's going to contribute to my pH. So then I can just take the negative log of that number to get my pH. So calculator again. And I got 5.12 for my answer. So again, just look at your salt, see what is the part that's reacting with water to produce hydroxide or hydronium ions, then write that equation. And then from there, it's just, a process that we've done in the past.